Science does not always progress the way we like to imagine it does. In the popular story of discovery, knowledge moves forward in a straight line. Observations are made, data is gathered, conclusions are drawn. Each generation of scientists builds cleanly on the work of the one before, adding detail and precision to a picture that grows steadily clearer. Progress is orderly, understanding accumulates. But the real history of science is full of moments when everything we thought we knew about something turned out to be wrong, not slightly wrong, not wrong in a way that required minor adjustment, fundamentally, completely, surprisingly wrong, in ways that forced scientists to go back to the beginning and ask not just what they missed, but how they were so confident they hadn't missed anything. Mimas is one of those moments. For decades, scientists looked at this small, battered moon of Saturn, one of the most visually distinctive objects in the solar system, shaped almost exactly like the Death Star from Star Wars with its enormous Herschel crater dominating one hemisphere, and reached a conclusion that seemed entirely reasonable given everything they knew. Mimas, they said, is dead. It is a frozen, geologically inert ball of ice and rock, preserved in deep cold, its surface ancient and unchanged, with nothing beneath its cratered exterior but more ice all the way down. That conclusion was not careless. It was supported by real evidence. It was the product of serious scientific analysis by serious scientists. It was, by any fair standard, the right answer given what they had to work with. And it was wrong. New data, gathered by the Cassini spacecraft during its extraordinary 13-year mission in the Saturn system, and analyzed using techniques that simply did not exist when Mimas was first studied, has overturned the settled picture entirely. Beneath the frozen, cratered, apparently dead surface of Mimas, there is an ocean, a liquid water ocean, global in extent, sandwiched between the moon's rocky core and its outer shell of ice, hidden from view so completely that it left almost no surface signature that anyone thought to look for. Today, we are going to ask the question that this discovery demands: how did we get Mimas so wrong? And what does getting it so wrong tell us about the limits of our knowledge and the genuine possibility that the solar system holds far more life-friendly environments than we have ever dared to imagine? To understand how scientists got Mimas wrong, you first need to understand what made them so confident they had it right. Mimas is the smallest and innermost of Saturn's major moons, with a diameter of just under 400 kilometers. It was discovered in 1789 by the astronomer William Herschel, the same William Herschel who discovered the planet Uranus, and named, following the convention for Saturn's moons, after a figure from Greek mythology. For nearly 2 centuries after its discovery, it was known only as a point of light in telescopes, its surface invisible, its composition uncertain. The first close look at Mimas came from the Voyager spacecraft. Voyager 1 flew past Saturn in November 1980, and Voyager 2 followed in August 1981. The images they returned were revolutionary. The first detailed views of Saturn's moons, revealing a diversity of surfaces and structures that no one had fully anticipated. And among the revelations was Mimas, its enormous Herschel crater, stretching across roughly a third of the moon's diameter, immediately drawing comparisons to the Death Star that were impossible to resist, and have persisted in popular descriptions of the moon ever since. But the Voyager images revealed more than just the crater. They revealed a surface that was ancient, heavily cratered across its entire extent, and apparently pristine. Heavily cratered surfaces in the solar system are a sign of age, a surface that has been exposed to the constant rain of impacts over billions of years without any geological process resurfacing or renewing it. When scientists looked at Mimas through the Voyager data, they saw a moon whose surface spoke clearly of geological inactivity. No smooth plains suggesting recent volcanic or cryovolcanic resurfacing, no fractures or ridges suggesting internal activity, nothing but craters, craters, and more craters. This was not surprising, given what scientists understood about the physics of small, icy moons. For a moon to maintain geological activity, to have an interior warm enough to produce tidal heating, cryovolcanism, or a subsurface ocean, it needs a source of heat. For small moons, the primary candidate is tidal heating, the flexing of the moon's interior as it is pulled by the varying gravitational forces of the planet it orbits, and, potentially, the gravitational interactions with neighboring moons. The key word there is flexing. For tidal heating to be significant, a moon's orbit needs to be elliptical, to vary in distance from its planet over the course of each orbit, so that the tidal forces change and the moon is repeatedly squeezed and stretched. This flexing generates friction, and friction generates heat. Mimas has a slightly elliptical orbit, but the amount of tidal heating that orbit should produce, given the size and composition of the moon, was calculated to be very small, far too small by any reasonable estimate to maintain a liquid water ocean beneath the surface. The calculations pointed clearly toward a cold, frozen interior, and the surface evidence confirmed it. And so the consensus solidified: Mimas was dead. The problem with the Mimas is dead conclusion was not that it ignored evidence, it was that the evidence it relied on was incomplete in ways that nobody fully appreciated at the time. The Cassini spacecraft arrived at Saturn in 2004 and spent 13 years conducting the most detailed study of the Saturn system ever undertaken. Its instrument suite was far more capable than Voyager's. Its observations were far more numerous. And over the course of its mission, it gathered data on Mimas that, when finally analyzed in full, told a very different story. The key discovery came from careful measurements of Mimas's rotation. This sounds, on the surface, like a dry and technical piece of data, the precise rate at which a small moon spins on its axis. But the way a moon rotates carries information about what is inside it. A moon with a uniform interior rotates in a specific, predictable way. A moon with a liquid layer inside it, a layer that sloshes and shifts as the moon orbits, rotates differently. The rotation wobbles in subtle ways that encode information about the internal structure that produced them. When scientists measured Mimas's rotation with the precision that Cassini's observations allowed, they found wobbles. Small but real deviations from the rotation pattern that a uniformly solid interior would produce. Those wobbles required an explanation. And when the team ran the calculations, they found that the explanation that fit best was not a solid interior. It was an ocean, a global subsurface ocean of liquid water located somewhere between 10 and 30 kilometers below the icy surface, separated from that surface by a shell of ice that had, until now, kept its presence completely hidden. The paper announcing this finding, published in the journal Nature in 2024, landed with the force of a genuine scientific surprise, the kind that makes you rethink not just one thing, but many things. Because if Mimas had a subsurface ocean, everything the field had concluded about which moons could and could not harbor liquid water needed to be re-examined. The obvious question, and the one that science writers and researchers immediately began asking, is why the ocean exists at all. If the tidal heating calculations said there wasn't enough energy to maintain liquid water under Mimas's surface and the ocean is demonstrably there, then either the calculations were wrong or there's something producing heat inside Mimas that those calculations didn't account for. The answer, as best as current understanding can provide it, appears to be that the calculations were not wrong, but they were based on assumptions about Mimas's orbital history that may not reflect the reality of how the moon's orbit evolved over time. Mimas's orbit may be relatively recently settled into its current configuration. In the past, on geological timescales, which is to say within the last few hundred million years, rather than the beginning of the solar system, Mimas may have been in a different orbital resonance with other Saturn moons, one that generated significantly more tidal heating. As that resonance ended and the orbit evolved toward its current state, the heating decreased. But oceans, once formed, do not freeze immediately. They persist. They are insulated by the ice above them. And the heat generated during the earlier, more active period may still be dissipating slowly, maintaining the ocean in a liquid state today. This is a story about orbital history and thermal inertia, about how the past state of a moon's orbit can leave a legacy that persists long after the conditions that created it have changed. It is a story that would have been very difficult to tell from the Voyager data alone, or from calculations based only on the current orbital configuration. It required the precision of Cassini's measurements and the analytical frameworks that developed in the years after the initial Voyager-era assessments. The implications of the Mimas ocean discovery extend far beyond a single moon of Saturn. They challenge the framework that scientists have used to decide which worlds in the solar system are worth investigating for the possibility of life, and they suggest that framework may have excluded possibilities it should not have. The conventional picture of where liquid water oceans might exist in the outer solar system was built around a small number of well-studied cases. Europa, the moon of Jupiter, has long been the poster child. Its smooth, fractured surface clearly indicating geological activity driven by strong tidal heating from Jupiter's powerful gravity. Its subsurface ocean, long inferred and now confirmed by multiple lines of evidence. Enceladus, the small Saturn moon discovered to be actively venting water vapor and ice particles from cracks at its south pole, has a confirmed ocean and is considered one of the most promising places to search for extraterrestrial life in the solar system. Titan, Saturn's largest moon, has a complex hydrocarbon chemistry and may have a subsurface ocean of water or ammonia beneath its thick atmosphere. These worlds earned their place on the list of ocean-bearing moons through abundant, unmistakable evidence. Their surfaces told the story of their interiors, and that is precisely why Mimas was excluded, because its surface told a different story, or appeared to. The surface said, "Nothing is happening here." The surface said, "Look elsewhere." The surface was wrong, or rather, the surface was right about what it was showing, but wrong about what could be inferred from what it was not showing. The absence of surface evidence for geological activity is not the same as the absence of geological activity. An ocean beneath 30 kilometers of ice may leave the overlying surface almost completely undisturbed, particularly if the ocean is young and the ice is thick. Mimas has had its ocean, according to current best estimates, for somewhere between 5 million and 15 million years. That is a very short time by solar system standards. The ice shell above the ocean may simply not have had enough time to develop the fractures, ridges, and smooth resurfaced plains that alert scientists to subsurface activity on other moons. The lesson is uncomfortable but important. Absence of evidence is not evidence of absence. A moon that looks dead on the outside may be alive on the inside. And if that is true for Mimas, a moon that was considered one of the most obviously dead objects in the Saturn system, it may also be true for other moons across the outer solar system that have not received close scrutiny because their surfaces did not invite it. There's another dimension to getting Mimas wrong that deserves attention. The question of how scientific consensus forms and how resistant it can be to revision even when new data begins to accumulate. The conclusion that Mimas was geologically dead was not simply a working hypothesis held loosely pending further evidence. It became, over the decades following Voyager, a settled piece of background knowledge. Something that appeared in textbooks, was repeated in review articles, and formed part of the implicit framework within which scientists thought about the Saturn system. When something is settled knowledge, it tends not to be actively questioned. It is assumed. And when data arrives that might challenge it, that data can be unconsciously interpreted through the lens of the existing consensus, rather than allowed to speak for itself. This is not a failure unique to planetary science. It is a feature of how human cognition interacts with established frameworks. Thomas Kuhn, the philosopher of science whose work on scientific revolutions remains one of the most influential accounts of how science actually progresses, described exactly this dynamic. Normal science, he argued, consists largely of puzzle solving within an accepted framework, adding detail, resolving anomalies, filling gaps. It is only when anomalies accumulate to the point where they can no longer be accommodated within the framework that a paradigm shift occurs, and a new framework replaces the old one. The Mimas ocean discovery has some of the character of a paradigm shift for the field of ocean world science. Not because IT overturns everything. Europa and Enceladus remain confirmed ocean worlds, and the broader framework of tidal heating as a driver of subsurface liquid water remains intact. But it challenges the specific assumption that surface appearance reliably reflects interior state. And that challenge has immediate practical implications for how the field decides where to look next. The question of where to look next is not merely academic. The search for life beyond Earth is one of the most significant scientific enterprises of the current era, and the identification of ocean worlds in the outer solar system has been central to how that search is being planned and prioritized. NASA's Europa Clipper mission, launched in October 2024, is on its way to Europa to conduct the most detailed study of that moon ever attempted. Its instruments will characterize the ice shell, probe the ocean beneath, and look for signs of habitability, for the chemical ingredients and energy sources that life as we know it requires. The mission was justified in part by the confidence that Europa's ocean is old, stable, and chemically complex enough to potentially support life. ESA's JUICE mission, the Jupiter Icy Moons Explorer, is also en route to the Jupiter system, targeting Ganymede, Callisto, and Europa. And proposals for a mission to Enceladus to fly through its water plumes and directly sample the material being ejected from its subsurface ocean have been under development and discussion for years. All of these missions were planned and justified using a framework that assumed we could identify the most promising ocean, worlds by their surface characteristics. Mimas has now demonstrated that this assumption is incomplete. Worlds whose surfaces show no evidence of internal activity may nonetheless harbor liquid water oceans. The question that follows is both exciting and slightly daunting. How many other moons in the outer solar system might have hidden oceans that no one has thought to look for? The candidates are numerous. Saturn's moon system alone includes dozens of objects, whose interiors have not been characterized in detail. Uranus and Neptune, the ice giants that remain the least explored planets in the solar system, have extensive moon systems that have received almost no close scrutiny since Voyager 2's brief flybys in the 1980s. If Mimas can harbor a hidden ocean despite its apparently dead surface, the case for a dedicated mission to the Uranian or Neptunian systems, long argued on scientific grounds, becomes even more compelling. There is something deeply human about the story of Mimas. Not because it is a story of failure. It is not, really. The scientists who concluded Mimas was dead were doing exactly what good scientists do, drawing the best possible conclusions from the evidence available to them, using the best analytical tools of their time, applying established physical frameworks that had proven reliable in other contexts. What happened was not that they failed. What happened was that the universe turned out to be more surprising than the framework allowed for. The solar system, it turns out, is more generous with its liquid water than anyone suspected. The conditions for habitability, the thing that gets planetary, scientists and astrobiologists most excited, are distributed more widely than the existing models predicted. Mimas sat there for decades, looking exactly like what everyone thought it was, a frozen, battered, geologically dead relic of the early solar system, remarkable only for its resemblance to a movie villain's space station. And all along, beneath 30 kilometers of ancient ice, a global ocean of liquid water was quietly existing, waiting for science to develop the tools to find it. The question Mimas now forces us to ask is not just how we got this one moon wrong. It is how many other worlds we are currently getting wrong in exactly the same way, confident in a conclusion supported by the evidence we have, unaware of what the evidence we don't yet have might reveal. The solar system is larger, stranger, and more full of possibility than the story we have been telling about it. Mimas is not just a corrected entry in a catalog of moons. It is a reminder that the most important discoveries are often the ones that force us to revise not just what we know, but how we know it. We got Mimas wrong. And in getting it wrong and then finding out we were wrong, we learned something about the universe that is far more exciting than being right would ever have been.